Okay, I think we can safely assume that this guy is going to accelerate this way down the plane, right? And this guy is going to accelerate that way, right? Furthermore, I think we're safe in assuming that there is tension in this cable just because an object in free fall will accelerate faster than an object on an inclined plane, right? So this guy is actually going to accelerate a bit faster than he would have if the tension hadn't been there, and this guy will accelerate a bit slower than he would have if there weren't this tension retarding his acceleration, right? Okay, so let's see. This guy is 4.3 kilograms, so that means that the force down is the weight, right, which is m times g. So 4.3 times 9.81. Let's figure that out. Okay, 42.183. And that's this force down, right? Okay, and then the force up is of course the tension in this cable, right? Okay. And then this guy here, let's see, what are the forces? I guess what you have here is you've got the tension in the cable, right? Plus you also have, what do you have? You have you have the parallel force, right? Like this, right? And the force parallel is mg sine theta, right? This angle here is allegedly 21 degrees, right? Okay, so we have 5 times 9.81 times sine of 21, right? So let's figure that out. Okay, 5 times 9.81 times sine of 21. 17.578. Approximately newtons. I'm going to store that baby in B just for fun. Okay, so we have actually, so this parallel force is actually a bit more than tension, right? So 17.578 newtons there. I'm just cheating because I know the tension's that, right? Okay, so golly, how do we do this? I think we do this for A. Let's do this. Okay, so for A, if we're talking about A, all the forces add up to tension plus 17.578. Right, notice that both of these guys are causing it to accelerate down the plane, right? And then that equals 5 times A. B, it looks like, what is it? It's just the weight, the force of gravity, right? 42.183 minus that tension, right? Equals 4.3 times A. All right, so now we're just simply going to add up these things. So this is 9.3A. And then we get here, if we add these together, we will get, usually we end up subtracting, right? But this thing actually, the t's go away, and you end up with 42.183. There are two protagonists, right? The weight and the parallel force, right? And then that equals 9.3A. Okay, so let's see. Let's see if I've got these guys stored. Okay, so alpha A plus alpha B. This is 59.76 equals 9.3A. Right, so therefore A is equal to 6.426. Right, so 6.43 seems to be spot on for that, right? Okay, but now we've got to figure out what the tension is, right? Okay, so what will we do? I think I'll just use this guy here, right? We'll use this formula. I'll rewrite this formula, right? T is going to equal 5A minus 17.578, right? So that's 5 times 6.426 minus 17.578. Okay? Okay, so that times 5 minus minus I guess 14.551. 14.5516. newtons, which I guess we'd have to say 14.6 newtons. Okay, so this one was weird in that you know, if this were a level surface and we're dealing with friction, we'd have parallel force and whatever, right? But it's not a force opposing the tension. It's actually a force helping the tension. What's interesting to me is that there still is a tension in the cable. This guy would, if it had his druthers, would accelerate down at 9.81, but it doesn't. It accelerates only at that rate. And this guy would presumably accelerate at a more leisurely rate than this, but the tension both makes this guy accelerate faster than he would have without the tension, and this guy slower. Anyway, I'm a physics teacher. I think stuff like that's interesting.